When we focus on that competitive style of mathematics, in the real world, that's not how maths is done. When we found that a student has a misconception, and what we've actually found is that they're capable of making generalizations. They're capable of math. So if we want something to be in a student's brain at the end, if we want them to understand it, if we want them to own it and be able to use it, then the mechanism for that going into their brain is that they have to use their brain to do the thinking.
I welcome you all to the Math Talks, where we go beyond formulas and grades and dive into what truly matters in your child's learning journey. I'm Dr. Garima, a math educator, mother, and co founder of Uncover Math Genius. In this podcast, I speak with leading thinkers, educators, and change makers from around the world to explore how we can raise confident problem solvers and not just high scorers. So, whether you're a parent, a teacher, or just curious about how children learn, you're in the right place. Let's reimagine math and education for the world our children are stepping into. So, today's guest is someone whose work has transformed the way thousands of teachers and entire school systems teach and think about math. I'm honored to welcome Tierney Kennedy, the founder of Back to Front Maths, one of the most respected conceptual maths frameworks in Australia. Tierney is known internationally for her work on misconceptions, cognitive conflict, and helping children move from surface level answers to deep understanding. She has authored more than 19 books, developed rigorous intervention programs, and her professional learning programs are recommended by multiple Australian state governments, including Western Australia and South Australia. What I love most about Tierney is that she doesn't just fix children's mistakes, she fixes the misconceptions that cause the mistakes. She helps children think differently, not just answer differently. And for parents who are listening today, this conversation will be such a gift because Tierney's work shows us that our children aren't bad at math. They simply haven't been given the chance to understand it deeply yet. So, Tierney, thank you so much for joining us. I'm truly excited for this conversation.
Thank you very much for having me. I was delighted when you reached out, and I am going to really look forward to speaking with your parents today.
Thank you so much. Okay, so Tierney, I want to start with something I see almost every day. Uh, Children are studying more than ever before. Parents are investing more than ever before again, and schools are covering more content than ever before. Yet children seem to be understanding less. It's not just in India, but I think it's a global problem. And I often call this the more work, less understanding crisis. So, from your work across Australian schools and systems, do you see the same pattern? And what do you think is really going wrong underneath it all?
Okay, that's a really interesting question. And I think Australia is a little different in that the idea of kids doing more work is perhaps not really happening. A lot of the time, I see kids actually avoiding doing work. In particular, they want to wait and have the teacher tell them how to do everything instead of doing the thinking for themselves. Uh, what is happening, I would agree, is less understanding. So when we look at, for instance, Australian PISA results, so PISA is an international test, and we can see that Australia has dropped through the rankings over the past 12 years or so. And that's a concern to me. So, in terms of what I think might be behind that, there are a number of different reasons. But I think the first one is to do with the idea of making somebody else do the thinking for me and kids not actually taking ownership for that thinking. One of the biggest change agents I've found in mathematics is just actually having kids do the thinking for themselves. So, if we want something to be in a student's brain at the end, if we want them to understand it, if we want them to own it and be able to use it, then the mechanism for that going into their brain is that they have to use their brain to do the thinking. And that's quite different to simply repeating what they've been told. Practicing something that you didn't think has some value. It really does. It helps with fluency, it helps build speed and accuracy. But if you want understanding to happen, then the kids really do have to actually do some processing of that information themselves as well.
Absolutely. And I think it's no more about filling up the worksheets now. You just have to dive in deeper.
Yes, as well. But I do think worksheets can be better designed to create thinking as well, I must admit.
Yes,
One of the things I see quite frequently is in something like a worksheet or a textbook, all the questions are phrased the same way. If
absolutely.
you've
I think
done
20 questions, the same type of questions.
That's right. So if you can solve the first question, then by solving the second question, you're not doing any new thinking, you're just repeating a process. And that doesn't necessarily build much retention, but it also doesn't build a lot of understanding. If
Absolutely.
instead you take a similar question or a similar topic, but you change the approach to the thinking that's done. So, for example, if we're starting with a rectangle and we're asking students to find the area for question one, question two, we could ask them to find the perimeter.
True.
And for question three, we could give them the area and get them to find the dimensions. And this approach is called using interleaved practice for a worksheet instead of blocked practice. And the idea is that students have to think fresh for each new question, have to adapt their strategy or think again. And even though it's the same content, it requires more thinking from students, which means it sticks in their head better.
I agree. I agree. That's right. But I think we're
Yeah.
we're laying a lot of focus on how many questions the students are able to complete in an hour's time, and so on and so forth. And I think that is the problem which is being created, and the kind of unnecessary pressure that goes on in the child's mind, the unnecessary competition that goes on around them, that also hampers their thinking ability. That's what I believe.
Yeah, well, it certainly did for me. I'm really good at maths. I wouldn't be in this role necessarily if I wasn't, but I was very, very good at maths at school as well. And I remember we played a game in class where called shootout, and you had to stand back to back with another student, and a teacher would call out a maths fact question, a
Mm.
multiplication fact or something, and you had to answer it quickly and shoot the other person down. Now, I won every single week, and it created a massive amount of anxiety for me as the person who was the best. And I think sometimes we tend to think of maths anxiety as something that happens to kids who aren't necessarily very good at maths
Absolutely.
or aren't very quick. But for me, I was quick and I was good, but I almost dropped maths altogether because of the anxiety created by games like that. So they work really well for some kids, but for other kids, not necessarily. It's not always a bad thing, but it's also not always a good thing. And I just think we need to be a little bit careful about that.
Other people,
Um,
yes. And I think this, on the contrary, I was never good at math. The only subject I was not good at in school was mathematics, and I think it was all because of the anxiety around me. So I did not take it in
mm.
a positive way. However, there was one teacher who changed my life, and that's what I always owe it to him. That he was the one who changed my life, my perspective towards mathematics, and I think it's all because of him that I went on to doing my PhD as well. I always owe it to him that he's the one. And there are kids. I did not take it in a positive sense. The entire competitive thing, though I was competitive. However, I did not take this math thing in very positive sense. So I'm sure if it is happening to me, it would be there would be so many kids around me who would be not taking it in a positive way.
I'm with you on that. And I think one of the things that happens is when we focus on that competitive style of mathematics,
Yes,
in the real world, that's not how maths is done. Maths is
absolutely.
often done in a team, and it's not like there's a time limit on it where you have to do a whole bunch of work in a really short period of time. No one's ever going to pay you to do that, right? Because we have a laptop for that. We have spreadsheets for calculations. And I think sometimes the way that we teach kids, we're not trying to raise a generation of mathematicians, we're trying to raise a generation of spreadsheets.
True.
And that's kind of crazy, it's not that it's not useful to be able to calculate. It is. It's great because it frees up your brain to do the more important stuff. But if
Yes.
we don't ever get around to doing the more important stuff because we're too busy doing the job of a spreadsheet, then I think we really rob our kids of a lot of the joy of maths and the thinking that goes on with it.
Yes.
I very much believe that all kids are capable of mathematics and probably quite high level mathematics. It's not that we're not born with different abilities and whatever, but what we learn and the way we use our brains is going to be far more important in the end than anything that we're born with. So, if we want kids to be able to solve problems, the way to do that is actually to give them problems to solve that are a little bit out of reach, not so far out of reach that they can't approach them, but a
Mhm.
bit out of reach, and ask them to do the thinking.
Right.
Um, One of the things I find that's really useful for parents and for kids to think about is, instead of thinking about mathematics as a problem to solve or thinking about problem solving, if we swap the word experimenting for the word problem solving, then it tends to work a whole lot better. So the idea is, have a guess, make a conjecture, or have a hypothesis, have an idea that you can test out, and then test it out and treat problem solving as though it's the first draft of writing. Try something out, see if it works, and then you can treat the result as, was it plausible? Is it busted or is it confirmed? A bit like, the show Mythbusters used to do.
Yeah.
And test it out, see if it worked. If it didn't, score a point for the testing and try again. Change
Yes.
your mind a bit.
This
Uh,
is beautiful, actually, what you said, that instead of problem solving, it is more of experimenting that the kids should do.
yeah. Yeah, I
That's
think experimenting with a new idea takes a lot of the scariness out of it, because it shouldn't be necessarily about getting it right first time round.
yes.
I tend to say to kids, look, it's not that it's okay to be wrong. I mean, obviously it's okay to be wrong, but it's more that if you're not wrong, if you already know this, it's too easy for you. You're not really learning anything by doing it. So what we want is something that's hard enough for you to get a bit wrong and have to actually go again and try harder and think more, because that's the thing that's going to lead to far more growth and far more success in the end than doing a whole bunch of stuff that you can already do. That's crazy.
True, true. In fact, what you just started with, that mathematics, the problems shouldn't be given alone. It's a teamwork which is supposed to be, and it's not just in mathematics. I think it is in every sphere of life that you're supposed to do a teamwork. However, our children are raised in a way that they're more competitive than being in a team. That's not a healthy competition, actually. So I think you learn a lot of life skills also from doing good mathematics.
Yeah, I would agree with you. A lot of the purpose of mathematics is to think logically, to be able
Yes.
to test stuff out, to be able to persevere when it's difficult.
True.
Yes, maths itself has a lot of components of things like numeracy that you need for everyday life and so forth as well. But I think really the value in maths is in the idea of perseverance when you don't know what to do.
Yes.
And that's, I mean, that's literally what mathematicians get paid for. No one's paying them to solve a problem that already has a solution.
Yes.
It doesn't exist, it's not a job.
Right. And now I think with the onset of AI and Chat GPT, getting solutions is such an easy job. Matlab, you just get it in a click of a, you just click it and you get the answer. What's the big deal in that?
Yeah, absolutely. But knowing, is that actually appropriate? Is there something here I can do to test it? Can I disprove this idea? That's really important. I
Absolutely.
think AI comes out with an answer. It's not necessarily a correct answer or a logical answer, but it's
Yeah.
worded really nicely so it sounds logical. And
Yes.
I think that's a big concern. We need to be able to throw numbers around and just look at them and go, hang on a sec, that doesn't look right. We need some estimation ability and some number sense to go, that number's way too big. There's no way that that investment is going to have a massive growth like that. That's just not real. Someone's trying to scam me, you know. And the same sort of thing is true with AI. So we need to be able to disprove as well as prove. And I think in most maths classes, we focus on getting it right, not on actually disproving something that's wrong.
Right.
And that for me is a really special area of interest. And that kind of led me down the path of kids' misconceptions as well.
Mhm. Right. Right. Okay, so I often see children in India struggling because they've picked up a misconception early on, and everything collapses on top of that. So, there's one misconception I really want to bring up because I see it everywhere, with children, with teachers, with parents, almost everyone. So, when we say something like, 8 divided by 2, the common understanding is that division reduces. So, when we divide, the number becomes smaller, and that is how everyone sees it as 4. Now, in reality, nothing actually reduces, nothing disappears. It just gets regrouped when it comes to a division. So 8 doesn't become less, it just stays 8. We simply reorganize it. So 8 divided by 2 it doesn't mean that 8 becomes 4. It just means that 8 is split into 4 groups of 2, and the total quantity remains intact. Only the structure of the regroup, I mean, the basically the group changes. The structure is just getting changed. And I find this so fascinating because this misunderstanding follows children for years. It affects fractions, it affects ratios, it affects their understanding of dividing by decimals, and even dividing by numbers which are less than one, which basically, according to me, breaks their mental model completely. So, Tierney, I'd love your take on this, as misconceptions are the heart of your work too. So, why do misconceptions form so early? And why do they survive so long?
Okay, well, that's quite a long question there. That has quite a long answer, but I'll see what we can do. The first thing I'd like to point out, though, is that misconceptions are not something that anyone's been taught. So, misconceptions don't come from teaching, they're actually a really natural part of development. Some researchers like to use the word alternative conception or naive conception instead. And the basic idea is that it's something that a student has realized happens, and they therefore make a generalization. They make a pattern. They notice, for instance, that when you do 8 divided by 4, then the answer is 2, which is smaller than the 8 that you started with. So they get this idea that division is making smaller because every time they divide, they're only dividing by whole numbers, and the answer is smaller than what they start with. But that doesn't actually mean that there's a problem. So a misconception I tend to think of as an overgeneralization. What that means is that they've noticed a pattern and then they've generalized, they've come up with a principle or a rule. They've just taken it too far and they haven't known when to stop with that idea. But it's really powerful because they've made a generalization. Now,
Yes. Yes, please go ahead.
now just to explain why that's important, algebra is generalized arithmetic.
Yes.
So generalizing is the basis for algebra. So when we've found that a student has a misconception, what we've actually found is that they're capable of making generalizations. They're capable of maths. So that's actually really powerful, but it's just that they're also wrong. And because they came up with the idea themselves, it tends to stick in their brain pretty strongly. As an example that parents might be a lot more familiar with, if you ask your students or your children to show you 5 fingers, they'll hold up their hand and show you 5. But if you ask them, how many fingers do you have? They'll count them to check. So even though they know it's called 5, they still count their fingers because maybe one day it might be different. So they actually don't necessarily have that concept of quantity. And quantity is a concept about what changes a number and what doesn't. For example, the only way to change a number is to add more to it or take some away, to operate it on it in some way. If you just move those number of objects around, it doesn't change how many there are. If you change the color of the objects, it doesn't change how many there are. If you put them in a straight line or in a circle, it doesn't change how many there are. They're just moving. But a lot of kids think that if you spread them out, there's more of them. Or if you move them around, it must somehow be different. If you put things in a cup and you shake them, suddenly there's more of them. And that's an example of a misconception. Because it looks different, it must be different. So it's important to understand that misconceptions aren't a problem.
Mhm.
They are, though, a limiting factor in terms of growth. So if we don't deal with them, then they do tend to stop future growth because kids keep coming back to the point that they believe. So we can think of misconceptions as a belief that a student has that conflicts with the actual meaning of the mathematics behind it, but it's one that they came up with themselves and it has some logic to it. As
Mhm.
another example would be, I was working with lots of little kids for a long time, 4-year-olds and so forth, and I asked them to draw a triangle. Now, if you think about a little student, a little kid drawing a triangle, they all end up drawing basically the same triangle. So
Mhm.
let's have a think about it for a sec. What kind of triangle do you think they might draw? What would it look like?
I think it must be an equilateral triangle.
Yeah, an equilateral triangle pointing up.
Yes.
And interestingly enough, and this was the bit that weirded me out, is that they all draw them green. Yeah, how weird is that, right? And uh, they're not wrong, right? So a triangle can be equilateral, it can be pointing up, and it can be green. But the problem happens when you turn that triangle then around 180 degrees, you flip it, then they'll say, oh, it's an upside down triangle. And you know exactly what they mean by an upside down triangle.
Yes.
But there's no such thing as an upside down triangle. It's not a thing. Right? Or if you take one of those sides and you stretch it and then you put the triangle on a funny angle and you change the color, then they're not so sure that's a triangle anymore.
True.
So that's what a misconception is. A misconception is an overgeneralization. They are right. It does have three sides and it can point up and they can all be equal, but that's not the only triangle. So it's an overgeneralized form. And the thing I find that actually helps with that is just to test it and say, okay, what about if we stretch this just a little bit? How about if we make a small change? Is it still a triangle now? Okay, well, no, not anymore. Okay, let's put it back. Is it a triangle now? Yes. And you can keep changing these sides just a little bit until they start giggling and going, oh, hang on a sec. It's still a triangle. How come? Because it still has three sides. And so you're coming back to that definition of what a triangle is. Likewise, if you're shaking, six blocks in a cup or something, and the kids think, oh, maybe now it'll be 10 because it sounds like there's so many, tip them out and count them and check and see and say, oh, it's still six. I thought it was going to be 10. And they're like, no, it's still six. And shake it again with the idea of trying to disprove the idea. I think one of the things that happens with misconceptions when we see them, and we do see them, but we tend to think that they're a mistake, that it's a fluency issue, that a student's just calculated wrong or something like that. We don't realize why they're coming out with those ideas, but misconceptions form patterns and they're actually common to students across the globe. So I've personally taught and tested more than 35,000 kids now, and misconceptions are really common, and it's always like the same 4 or 5 ways in which a student is wrong, which is very cool. But because it's a pattern, that means it's fixable, which is awesome. But it's not fixable unless a student realizes that they're wrong. So by experimenting with their idea and testing it out, then they go, oh, hang on a sec, it's not working. All right, now we can work out the right one. But if you just leave it there and try and lead them to the right answer instead of testing their own idea, then it tends not to go very well and they just forget really quickly. So 2 weeks later, it's like you never taught it.
So I
Yeah.
think it's the job of you have to, the teacher or the parent has to really facilitate this pattern, and somehow I believe that it's the push which is required from the parents or the teacher's side for the
Yeah,
kids.
I tend to find the best way to start when a kid comes out with something that's just a weird answer is just to say, okay, let's check and just test it with them. Just try it out. If they think that, one half is bigger than the other half, just put them both on top of each other and check. If they think that if you cut, for example, a parent I was working with was making her daughter sandwiches each day for lunch with 2 bits of bread and cutting it in half to put in her lunchbox to take to school for lunch. And her daughter kept saying to her, Mum, please don't cut my sandwiches into triangles because I can't fit it in. And her mum was saying, that doesn't make any sense. It fits in your lunchbox just fine. The bread fits in your lunchbox. There's not a problem. But her daughter wasn't saying it doesn't fit in my lunchbox. She was saying it doesn't fit in my stomach. So she was thinking that if you cut the sandwich into triangles, that it's more bread than if you cut it into rectangles, because the triangles apparently are bigger than rectangles.
But I
How
love the
weird
way
is that?
she
Yeah.
yeah,
So
they
that
are
kind of
very
thing.
nice.
Yeah, she, it was like she thought that there was more bread coming out of the knife when you cut it, that somehow it actually made more sandwich, not that it fit differently in the lunchbox. So, yeah, that's the kind of thing that sounds just insane
Yes,
to
yes, yes.
us once we're past it. So, once we've passed that idea, we just can't even imagine that kids would think that. But it turns out they do. It's really common.
Yes.
So I have probably 80% of kids who are about 7. If I take a rectangular piece of paper and I fold it into half in different ways, so I could do it diagonally instead of horizontally or vertically, they think that the diagonal halves are much bigger than the rectangle halves, even though we started with the same piece of paper, and they can see that the two triangles fit on top of each other. It's very weird, but it's really common. So, yeah. In terms of the idea of dividing before, one of the things that happens with division is that kids aren't understanding the idea of how many. When we learn division as primary school, we tend to work on a partition model, which is uh, 8 split into or partitioned into 2 groups of 4. Whereas a model that transfers better for high school is how many twos in 8.
Yes.
So that way you can think of things like if you're trying to do 8 divided by a half, 8 split into half, like that doesn't really make sense, right? Whereas if you're talking about how many halves are in
In
8,
yes.
then you can think of much more easily. So in Australia, we have money we have a dollar coin and we have a 50-cent coin, which is half of a dollar. So we can think, okay, well, if I've got $8, right, how many half dollars would be in that $8? And that makes a lot more sense. Or how many $2 would be in that
Yeah,
$8? Yeah.
right. I think that makes more sense. So that's why we always say that mathematics is a language because there's a universal definition for division, and I think for every operation that exists.
Yeah, yeah, absolutely. And I think sometimes the model that we use is important. Another example is, I guess, in high school, a lot of teachers talk about algebra as fruit. So apples and bananas, and you can't add apples to bananas. But then that breaks down as soon as you try multiplying or dividing. So I think we need to be a little bit thoughtful about what models we choose to use. And whatever it is, it should always work, not only sometimes. Yeah,
Yes, right.
yeah.
Okay. So one thing that I love in your approach is the cognitive conflict, gently disrupting a child's assumptions so they rethink and they do not repeat. So I too use this, a lot of times in my teacher trainings as well. And I've seen children transform when they're allowed to reflect instead of rush. So, for parents who are listening, Tony, let's explain cognitive conflict in simple terms, and maybe both of us can give some examples to attach to this.
That sounds good.
Yes.
Okay, well, for me, cognitive conflict happens when a student thinks something will work and then actually it doesn't really. So the evidence when they try it shows something different. An example might be in science. So, say for instance, I've got a really cold glass of water and I get it out of the fridge and I put it on the bench on a hot, humid day. Then what happens is on the outside of the glass, this water forms, it condenses on the glass. But if you ask kids, so where did that water come from? They think it came from the inside of the glass, like it got sucked through the glass and stuck on the outside. Instead, cognitive conflict would be instead of explaining to them, well, that's not going to work, it came from the air, cognitive conflict would be setting up an experiment to disprove what they were thinking. So, for example, if I took an empty glass from the fridge and stuck it on the bench, condensation would still form, at which point it clearly didn't come from the water inside the glass, it had to come from somewhere else. So it's the idea of introducing something to make them rethink and go, hang on a sec, my idea might not be correct. I don't think that actually works. I might need to think again. I tend to do that by questioning, by asking them some questions that get them to rethink. But that can be done in lots of different ways, and it's useful in lots and lots of different subjects. It's just not often done in maths. How about you? What do you tend to think of as
I think
cognitive
I'll stick
conflict?
to mathematics for now. You gave a beautiful example. I'll try to, reinforce my thing as well. So I see that, most children very confidently, they say that 3/7 is bigger than, half, because uh, 3/7 is actually because it is made of 3 and 7. Both are bigger than 1 and 2. And I never correct them immediately. I I simply take them, I take equal length two paper strips, and one I cut into 7 pieces, and the other one I cut it into 2 pieces. And then I ask them to pick up 3/7 and 1/2. And suddenly there's this moment that, you can almost see the conflict forming. Their mind actually realizes that yes, half is actually bigger. So what I believed was wrong. And
Yeah,
that very
absolutely.
part, yes, is the moment that misconception begins to shift.
Yeah, I can use a similar idea but with whole numbers. So, one of my favorite tasks is to draw a line across a page. And at the start of the line on the left, write the number one. And then on the right of the line, write the number 1000. And just get them to write on the line where they think 10 goes and where they think 100 goes. And this is a really important test. It's about the idea of relative size. So they should think things like, well, 100 is really small compared to 1,000. So it needs to go much closer to the one. But often they put it in the middle. And I could say, hey guys, but what about the 500? Where's that going to go? But that doesn't help all that much. What helps a lot more is to say, okay, here's 200, write that one on now. Now 300, now 400. And then skip up and say, well, how about 800? And at that point, it's getting very squishy. And they're trying to write all these numbers in this space. And I'll say, does that look right to you? And my go to question, I guess, the idea of getting kids into cognitive conflict, you can tell that they're in cognitive conflict because they have a change in their expression. So you can actually look at their face and see. And what you're looking for is the idea of surprise. So they might raise their eyebrows or open their eyes really wide. They might start compulsive fidgeting. So they're suddenly stabbing holes in the piece of paper or ripping something into shreds. Or they might giggle. So sometimes they go, that's not right. And you can see that they're looking at it and thinking, hang on a sec, there's something weird going on there. When I see that, that's a really good sign because it means that they're realizing that something is not making sense there. So at that point, I'll usually say, does that look right to you? Instead of saying, can you see a problem with that? Because can you see a problem with that is a really confronting kind of way of saying something. And they'll say, no, there's no problems. I'm fine. Whereas if you say, does that look right to you? They go, no. Which bit looks funny? That bit there? How come? Because they're kind of all squished up and there's all this space. Okay, let's go again then. And just redraw the line and say, okay, have at it. Try again. Put on 10, put on 100. And the weirdest thing is, they get it wrong in the exact same way that they just did before. And it often takes 8 or 10 goes for them to realize, hang on a sec, this isn't actually working for me. It's not ever going to work. And they start moving the 100 much closer to the one, but they still usually leave a really big gap between the one and the 100. Because, see, you've got to leave room for all those tens and they haven't really realized there's tens between all the other numbers as well. So if I give them 110 and 120 and 130, then they go, oh no, it's not going to work. And they shift the whole thing.
Yeah.
But at that point, once they've actually really genuinely changed their mind, then I can lead them about the 500 and it will stick. But if I try to lead them to 500 being half of 1,000 and therefore being in about the middle between 1 and 1,000 or between 0 and 1,000, before they've realized that 100 won't ever be able to fit in the middle, then they try to remember two things. So cognitive conflict happens when a student is trying to remember two things at once that both can't be true. they have their idea, which is 100 is in the middle because it's a pretty big number. And they have the idea that we're leading them to, which is 500 is half of 1,000. So it goes in the middle. They're
Mhm.
not going to remember both long term. So what happens is then if we try to build on it, one of them they're going to forget. And the thing that they're going to forget is the one that they didn't think themselves,
Yes.
right? The thing that they didn't come up with, the idea that we just told them. And I think sometimes we focus far too quickly on leading them to the right answer because we think that's the be all and end all, instead of actually getting them to test it out and disprove a wrong idea before we try to teach them the correct idea. Yeah, so that's cognitive conflict in a nutshell.
So I think that's cognitive conflict is very effective in that sense. And
Yeah.
so can you tell how parents can use these small moments like this at home to, gently challenge their child's thinking without making them feel wrong?
Well, okay, there's a good answer to that, but the big thing I would do is be okay with being wrong, to be honest. So I tend to do the not, it's okay to be wrong. It's essential to be wrong. If you're not wrong, you already know this. I need a harder one. Come on, we can find a good, tricky one. Let's have a go. And the idea of actually trying something that's a bit too hard and say, well, I haven't shown you this yet. Of course you don't know. That's why we're experimenting at the start. One of the things I find is really useful is actually just to ask them questions that are a bit too tricky and say, look, this probably isn't something you've learned at school. This probably is something that's a bit too hard, but let's try anyway.
Mm.
And uh, actually just giving them questions that are a bit tricky and then helping them think it through. But when you do that, you have to allow time because it always takes about twice as long as you're expecting. And it's really easy to get frustrated when a kid is not getting something. So the idea of what I do is I actually score points. So this sounds a little odd, but I have different rules from when I'm doing problem solving with kids in class to when I'm doing the more fluency or computation side of things. On a lesson where I'm doing problem solving, I have these 5 rules. So the first thing I do is tell them, this is going to be hard today. It's not going to be easy because if it's too easy, you already know it. So we're going to be experimenting with stuff you don't know today. So be okay with that. And that means our first rule is that the answers today don't count for any points at all. So they're worth no points, the answers. So that's rule number 1. Rule number 2 is what does count for a point is having a guess or making a conjecture. So when you have a guess, you score a point. Whether or not that guess is right or wrong, I actually want you to have a guess, have a hypothesis, have a try of something first.
Yeah.
And then rule 3 is once you've had your guess, you have to test it out. So test it out, and the testing scores another point. So whether you were right or wrong, you score another point because you tested it.
Mm.
Now,
Correct.
if you were right, clearly that question was too easy, so we need a harder one. So then you can have another guess and keep going. But if you were wrong, you get to have guess number 2. And that means you score another point for your guess and you test that one out and score a point for that one as well. And basically, that's because the more thinking you do, the more points it's worth. So it's not about the answer being the most important thing. We're actually valuing the process. And for me, that process works really well. For me, the 4th rule when I'm working with a class of students is once you've had your first guess at a question, you're welcome to work together and copy as much as you want because the answers aren't worth any points anyway.
Mm.
Copy away. And if you can think of 2 things with your friend, like try both of them. If you can think of 3, try them all. And so we're encouraging that collaboration and cooperation and actually
That's
thinking
beautiful.
together.
Yes, I
Yeah.
think that's a beautiful takeaway for the parents, actually.
Yeah. And my last rule is usually when you change your mind and you realize something was wrong, don't erase it, don't rub it out.
Yes.
Just change colors and go again because I actually want to see when you're changing your mind. One of the little tricks I use for that is instead of crossing it out, because a kid always wants to cross it out or rub it out or something to erase the mistake. One of the things I found works instead is to draw a little circle, like a checkbox next to it, and tick or check that box to say, hey, I've evaluated this one and found the mistake. So it's not a tick because it's correct, but it's a checkbox next to the mistake to tell you, no, hang on, I've changed my mind on this. And that's worth a point. So don't rub it out. And I mean, there are some other things I do with teachers that maybe don't work quite as well with families. One of them is don't use a book to do maths, use scrap paper. Right. So I used to do maths with my kids at a restaurant. We would go to church on Sunday mornings, but before church, I would take them out for breakfast to a restaurant, and they had paper napkins or serviettes. I'm not sure what you would call them. So I used to take a pen in my bag and we would use the paper napkins and do maths on paper napkins. They're
Right.
much happier with being wrong on something that's clearly rubbish.
Right.
They're okay with being wrong on scrap paper, but if you do it in their book, then it's much more scary.
Yes.
And likewise, the other tip that works really well is when you change your mind, change colors. Just try to use all of these different colors. And that even worked for 14 and 15-year-olds. I remember these big boys in year 9 or 10 saying to me, I used the whole rainbow today, miss. And I was like, well
But
done,
that
you
makes
had
your
no
life
idea.
colorful. That makes your life more colorful.
Yeah, that's right. And I think just the idea is reward what you value.
Yes.
Right. I
I
think
think
if we want to value changing our mind and testing things out and being okay with being wrong, then we need to make that a really obvious process. So reward what it is that's valuable in maths today. In a different day, I might reward the correct process and putting all the steps and remembering to write meters squared at the end and whatever, but not on a problem solving day. On a problem solving day, it's meant to be hard. You're meant to be thinking and changing your mind. So, setting those really clear expectations at the start is very helpful. My kids knew we're in a restaurant using napkins. Of course, we're doing mucking around maths, not formal maths. Now is not the time to do multiplication facts. Now is the time we're testing stuff out. Yeah.
yes. And I think it's the same with me. I used to take my kids out for their classes while in the car because earlier we usually don't get time together because I'm working in the morning and they're having their own classes. So it was usually in the afternoon or the evening when I used to drop them off for their different classes. That's when we used to do maths. And they never knew that maths is supposed to be done with books. They always knew that Mama is supposed to ask questions and we're gonna think together and maybe and basically that's when I realized that one concept is not for a particular age. You can have the kids can learn about linear equations much early in life than doing it in sixth you know
Absolutely.
yes,
My my kids were doing quite complex operations with fractions before they started school,
yeah.
and I don't know. There's lots of ways you can set things up by just asking a question instead of telling them.
Yes.
So, how long is it until lunch? That's a good question. Well, we're going to eat lunch at midday. You work it out, right? And that kind of idea of letting kids actually have a try. When I was going grocery shopping, I would say
Yeah.
to the kids, right, you get 6 apples and put them in the bag, right? And they would go and have to get 6 apples. And when they came back and they didn't have six, I could say, yeah, that's not six. Go again. You need more. So I think there's lots of opportunities just as part of normal everyday life to
Yes,
involve mathematical thinking. Yeah,
absolutely.
in a way that's not necessarily big and scary and whatever. And I think that's the opposite experience to what a lot of parents have had when they were at school.
Yes.
So, unfortunately, a lot of the way maths has been done is to basically tell kids, well, you are clearly stupid because you can't follow what I'm saying and you can't do it really quickly. So, there's something wrong with you. And I think that ends up with people thinking that maths is somehow genetic. Apparently, everyone can learn to read and write, but not maths. Like, that makes no sense. It's
I
not
think that
how
fear also
intelligence
travels from
works,
the
but
parents. The fear travels from the parents also to the kids. When the parents
it
say that they
does.
don't know math, the same happens with kids. And I think it's a very they say very proudly out there that we don't know maths, and that's okay. Nobody would go out and say that we don't know English, but everybody is proudly saying that we don't know maths.
Yeah, I tend to talk to parents at that point and say, look, I'm really sorry that someone made you think that you were not capable of maths. You really were. And I promise I will never let your kid think that. So you back me up at home as well, but I will never tell your kids that they are not capable of maths, because they are. They're capable of really high mathematical thinking, and I'm going to make them do it. So don't let them opt out. Don't let them take the easy route. Make them think. It's not bad for them. And I mean, in life, who doesn't fail at stuff, right? Like, I think I guess the reason that I am good at maths is mostly just persistence. So I tend to think of a problem that I haven't solved yet as just a plot twist. So, I mean, maybe I won't be able to solve this. Maybe it's just a plot twist. Maybe I'll get there eventually. I'm just building the character along the way. There are very few problems that don't have solutions, certainly that kids are dealing with. As an adult or doing mathematics in the real world, well, that's a little different. But I think sometimes also we don't model that kind of maths for our kids. When you think about it, we, our kids, model for maths, not what we say, but the maths they actually see us do in front of them. And this hit home for me when my kids were younger. And I remember my two little boys running into the bedroom while I was doing a Sudoku puzzle and saying, "Mummy, are you finished?" And I said, "No, it's a hard one." And they ran back out. And they came back in like 2 minutes later. I hadn't put in any numbers and said, "Aren't you done yet?" And I said, "No, it's a hard one. It's going to take me a bit." And they came back again like 3 minutes later. And I ended up flipping through my Sudoku book with them and going, "Look, some of these I haven't finished, like I haven't solved. And here are some that I've put across through because I got them wrong. And here are a bunch that I've solved." I might not be able to do it. I might get stuck. And I remember my son saying to me, "But Mummy, why would you do it if you don't know that you could get it right?" And that just floored me. And I thought, oh my goodness, my kids have the wrong view of maths here. Like, how does anyone else have any hope? And I said to my kids, "But that's what makes it fun. It's only a puzzle if it's tricky and you don't know for sure you can get it out." But that really changed my approach to parenting maths. So one of the things I started doing was I have a friend, Michael, who's an actual mathematician, but he publishes these puzzles called curios, Michael's curios, and they're visual puzzles that look like raindrops falling out of a cloud or some coloured jewels all lined up or something. And there's no clue for how to solve them. But the idea is that all of them have some kind of maths behind them and you can figure out a code. So if you work out what the code is, so for example, the first one I solved was distance between raindrops was either a 0 or a 1. And I therefore was able to work out that it was a message in binary and translate it and then figure out what it says. And if you are the first person to solve it, he names the puzzle after you and puts it on his website. And I thought, right, that's it. I'm going to download one of these and have them in front of my kids that I'm working on so that then I can model what I do when I don't know. Yeah. So the first one that I solved took me 18 months to solve, right? Not like I was working on it every week or anything. I would leave it for a couple of months at a time and then come back and try some more stuff. And my kids would be able to see that there was maths that I didn't have a solution to yet. Mm. So they understood that maths was more than what their mum knew, and that I was doing that on purpose because it was fun and interesting, not because it was necessarily the best use of my time or anything. And that maths wasn't about having all the answers to questions that people have seen before. It was literally maths is what you do when you don't know.
When you don't know, right?
Yeah.
Nice. So I truly believe that children are, they're scared of being wrong and not of math. So what do you think this fear starts? Where do you think this, the entire thing starts?
Oh, that's possibly more of a question for psychology than for me. I expect as humans, we don't like being wrong. Like as adults, we don't like being wrong in public, right? It's not a thing. Nobody enjoys it. But actually, so it's a really unrealistic expectation to think that somehow a kid is going to go, yes, I'm wrong. That's great. Let's go again. That's never going to happen, right?
Yes.
But the idea of course you're wrong. You don't know this thing yet. I haven't shown you it yet. I want you to try and figure it out because actually you might figure out something new and you're going to learn how to figure out stuff when it's hard. That's important. So I think maybe taking the fear out of being wrong is more important.
Yes.
And one of the ways we do that is to model being wrong, not faking it, not setting it up so that then we can go, oh no, I made a mistake and you can correct me and it's all fine because they know that's pretend. But I think the way to model it is to actually try hard stuff ourselves and to share the frustration and to share all the doodles of us trying different ideas. If you think about it, when a mathematician hands in a paper, the paper isn't the way they got there. The paper is the final edited version that's beautiful and logical and the most efficient or whatever. That's never how they solved it though, right? So we have to model the solving, not just the end product. If we
Yeah.
model the process for kids, they're more okay with being wrong. And we have to be okay with being wrong if we want our kids to be okay with being wrong.
Yeah.
Yeah.
Nice. Okay. So, again, one thing I love about your work is your belief that wrong answers are not mistakes, they are windows into thinking. I mean, I feel the same because wrong answers tell us more about a child's mind than right answers ever can. So, how do you approach wrong answers?
Well, for starters, your idea there of wrong answers tell us more about a child's thinking than the right answers. You're right. There's actually good research to show that. So, the research on formative assessment uh, by a whole range of people, but Dylan Willem is, one of the big names in that field. The research on formative assessment isn't done on a test of questions that all look the same that kids can get right. The research around it is actually based on the idea of asking kids a question that's hard enough that they get a bit wrong because it tells the teacher, something's going on here, or it tells the parent, something's going on here. And as long as we know that something's going on, we actually almost automatically do something about it, which makes the teaching more powerful. So rather than starting with an explanation, here's how to do it, start with a question. What do you think you might try? And then adjust your teaching from there. And it tends to work a whole lot better. But I think I've missed some of what you were asking in that question. So I might get you to say again. Sorry.
Yeah. No, no. Sorry, I didn't get. You asked me the question again, but I think what you're explaining is absolutely right. I mean, just want to have an insight of how do you approach, the wrong answers. What happens in there?
Yeah, okay. So there are a lot of ways around it. If a student's scared of getting it wrong, then I talked to you before about the rules, but one of the ways that I find is really cool to actually help them out when they just get kind of stuck is to offer something called an enabling prompt.
Yes.
So, an enabling prompt is used particularly when a kid is just sitting there fritzing and they can't work out how to start. So, as an example, if I asked you, right, I want you to write a story about anything you want, then you sit there having no ideas because it's too open.
Yes.
One of the ways to help kids with that is actually just to suggest something to bounce off. So, for example, it has to have a frog in it. They fall down a hole. The whole first sentence has to start with the letter Z. Anything to kind of bounce off. And for me, one of the things that's a really good bounce off point is actually a wrong answer. So, one of the things I do is to say, all right, give me a wrong answer instead of a right one. But I want an answer that's too small. What do you think would be too little? Okay, now what would be too much? All right, now what do you think might work? And so the idea of actually disproving a wrong idea is really powerful and it gives the kids lots of things to try.
Yes.
Another one that I like is I play two lies and a truth with kids. So I give them three answers. And the idea is that they have to prove two of them are incorrect. So rather than finding the right answer, the aim is on proving the wrong ones are wrong. That's a lot of fun. Sometimes I give them two wrong answers and one right, but sometimes I also just give them three wrong answers and they just have to prove two of them are wrong, which is always a lot more fun. And then they'll come to me and say, "Oh, Mrs. Kennedy, you didn't give me the right one." And I'll say, "I know, but now you know what it is, don't you?" Ta-da! And they really enjoy it. So I think sometimes just giving them the answers is not a bad idea. Another idea that I find works really well, the fancy name for it is called using deductive reasoning. And deductive reasoning is working backwards. I tend to call it checking with Bob. Now, Bob is back of book. So if you think about most textbooks tend to have the answers in the back. One of the easiest ways to get started with this type of thinking is just give them the question and the answer and say, how did I get it?
Yeah.
So it takes all the fear of being wrong out of it. They're not worried about that anymore because they know what the answer is, and the aim is to prove and disprove rather than something else. I find that those approaches, once the answer is not the be all and end all, once it's not the most important thing, then you can use it as a tool instead. So let them use it and work backwards, let them disprove a wrong one, all of those kind of ideas. And kids get really excited and far more into it than they would otherwise.
Yeah, but then I think when it comes to, when they're telling their answers from the back answers, that's what some of the kids get demotivated also, because I see a lot of kids coming to me and asking, Ki, this is the answer which is written at the back and that is supposed to be correct. However, I'm not getting the correct answer. So you have to
Yeah.
actually facilitate their that situation now. And I, according to me, so visualization plays a major tool in what I do actually with the kids. So I asked them to visualize the entire thing. So when it comes to, so most of the maths that I've done for the primary level, for the elementary level, I've done it with my kids. Okay. So I also believe that a lot of word problems have to be told, something which is surrounding you, in your day to day life. You can take the word problems from there, and without even telling them this is the concept that you have to use, you just have to tell them, let them be, and just enjoy with the problem. Just visualize the entire thing, and I think that just kicks off their learning again. And again, there's no right or wrong answer to that. You just have to enjoy the entire process which is there.
Yeah, I'm with you on that. And I tend to use a couple of different visual models for that. For me, the most important one is probably an array. So the idea of, if you imagine Lego blocks, the top of Lego, how it's arranged into rows and columns, or a grid, or tiling or anything like that, it tends to form squares. So the idea of thinking in rectangles is really important, particularly for multiplying and dividing. But it's also really important then for anything to do with fractions and algebra later on. When
Yeah.
I'm working with little kids, I tend to use more of a bar model or a strip of paper that you
Yes.
can break up into different parts. So if I was thinking of something like, all right, I went to the shops and I paid money for lunch and I also bought two other things. And at the end of the day, I had some money left. How much did I start with? Or how much did I have left, or whatever. And you can basically just draw it out. So you've got a strip of paper that represents the amount of money you started with. And then you write on the amount that was for lunch. And then you write on the two things that you bought. And you say, right, well, how big is the other one? And so it's not necessarily about writing an equation with numbers
Yes.
or a number sentence. It's more about thinking about your, what parts do you have and what are you missing? Are you missing the whole or are you missing one of the parts? How do you work forwards and backwards? And that approach is really important. I must admit, not a big fan of word problems. I tend to think that they're not all that useful in the real world. Application, yeah, but my just to tell you a bit of a story, my my parents really like mangoes, and we live in a tropical area where mangoes grow. And over Christmas, they bought two crates of mangoes, which was about 600 mangoes. And they had them, about 400 of them at a time, covering their bed, just piled up there's mangoes. And I thought, oh, mum, you are the person from the maths problems, because you always see these stupid maths problems that are like someone bought, 15 watermelons and then another 20 watermelons. And you think, who on earth bought 35 watermelons? It's not a thing. But apparently my parents bought 600 mangoes. So, yeah. Uh, Instead, I tend to think more about the real context that we're in and is there something that needs solving. So, for example, rather than doing a word problem with a little student, with a little kid, what I would say is, we're going to have our grandparents over for dinner. I need you to get out the right number of plates, and just leave it. So then they have to figure out, well, how many plates do I need? That's a good question,
Yes.
right? Or those kind of ideas. I've actually got heaps of them on the Back to Front Maths website. So if anyone's looking for them, if they just jump on Back to Front Maths, just Google it, and in the search term, you can type in the word parent, and there'll be a bit called parent page or parent portal. And there's heaps of different ideas there that you can download just for doing maths at home with your kids, that aren't complex, that aren't really difficult, but that just build in maths as part of everyday life, like getting out the right number of plates, or serving afternoon tea, or sharing up food between people, or something like that, rather than how many watermelons did that person buy and what speed was the train moving at. So, yeah,
That
hopefully
is
that's helpful.
all around us. If I go back to the COVID times, I taught both my kids fractions in the kitchen itself.
Yeah, absolutely. I actually have written 7 weeks of at home maths program on that website for free as well. You can get to it from that same parent portal. And one of them was fractions, one of the weeks. So it's for, in Australia, it's like kindergarten through to year 7. So that would be kind of the first 7 or 8 years of school.
Mhm.
Yeah, and there's 7 weeks worth of maths at home ideas there, and it's everything you can do in a kitchen with your measuring cups and things like that. Not so you don't need fancy resources, and it's all free, with little videos and things. So feel free if that's helpful. But yeah,
Yes.
yeah.
So we come from such different systems, yet the core problems are so similar. What do you think India could learn from Australia, and what could Australia learn from India?
Oh, I don't know probably enough about the Indian system to necessarily be able to advise that. But I think one of the things that I think education as a whole could really learn is that no one approach does everything. So I tend to work on a lesson cycle rather than on, are we going to do explicit type teaching or are we going to do inquiry type teaching? We don't need to settle for one or the other. We can actually do both and get all the benefits instead of just some. One of the things that happens in that I see in Australia and in Canada, in the US as well, where I work a little, and in some of the European countries, is that teachers tend to stick with one approach to maths teaching. So they do everything as a problem all the time, all contextual all the time, and none of the uh, fluency, drill and skill type stuff. Or they go the other way. They do everything as, I'm going to show you, and then you're going to practice that exact thing until you are really quick at it, and none of the idea of problem solving. All of the approaches have pros, all of them have really good things for them, but they all also have cons. And when you only use one, then the issue is that you don't get the balance, you don't get the benefits of both, you only get one. So the big thing I found for working with any system, any teacher, any school, is that if you want maths growth to happen, if you want better results, if you want faster growth, usually what you have to do is give up a little bit of the thing that you like doing, a little bit of the thing that you're good at, in order to do the opposite approach that you usually don't like doing or don't really agree with. Because actually, maths is more than one thing. Maths is more than just problem solving, but it's more than just fluency. It's more than just numeracy. It's also a dance. It's also beauty. It's also logic. It's also a language, like you spoke about before. So if we only do one type of maths, kids only get good at that one type of thinking or that one type of calculating.
Mm.
And we actually need rounded kids who enjoy it and can do lots of different things. So don't be afraid to try something you haven't done before. Of course, you'll mess it up, but that just means you can be their model for testing stuff out and learning from mistakes. So that's not really a bad thing either. Yeah.
Nice. So, this is one thing which I always ask my guests. If a parent is listening and feels inspired but unsure where to start, what is that one ritual you would want them to begin tonight?
All right. The one thing I would like all families to do is to actually ask kids a question before you know the answer and just play with it together and try it out. Uh, Remember to draw the maths. Don't just write the numbers. So drawing them out, moving it around, understanding what it looks like, and to apply some logic to it. So think stuff like, if a kid's not getting it, make the numbers easier, but keep the thinking hard. Keep the thinking the same, but just reduce the cognitive load by reducing the numbers. Don't always focus on having to know. You don't have to know. You can always look it up or whatever. Find the answer and work backwards rather than necessarily starting from an explanation. Um, yeah, but don't be afraid of maths. It's just experimenting. Just have a play with it and muck around with it and have some fun, and see what works and see what doesn't, and score your points for both.
And I think it can be a teamwork as well, both the parent and the child working together. Yes.
Yeah, absolutely. I tend to find that the best maths happens when a parent says to their child, "Yeah, I don't get this yet," but they add the yet.
Yes.
Not, "Oh, I just won't ever get this." Well, let's learn it together. Let's work on this together and see what we can figure out. You try something, I'll try something, and we'll talk about it together and see.
Absolutely. And the
Yeah,
journey is beautiful.
yeah, absolutely.
Okay. So, Tierney, thank you so much for this incredible conversation. And this talk has, reinforced the belief in me that math understanding is not an accident. It's something we build deliberately, patiently, and joyfully. And to all the parents who are listening, I hope today you got the message. Your child is not behind. Your child is not bad at math. Your child is not lacking any kind of ability. They're simply waiting for the right kind of understanding, the kind we discussed today. So, if something in this episode made you pause, if it made you rethink a belief that you have carried for years, if it made you feel like this is what I want for my child, please share this conversation with someone who might need it right now. It may be a fellow parent, a teacher, a friend who's struggling with their child's learning. Because the more we talk about misconceptions, thinking, and curiosity, the more children we can help together. So, Tierney, thank you for your generosity, your clarity, and your heart for children. It's been such a privilege to have you here. And to everyone who's tuning in, learning is not a race, it's a relationship. And you get to build that relationship every single day and every single moment. Thank you for listening. Until next time, stay curious, stay kind, and keep learning alongside your child. Thank you so much.
Thank you.